Hello friends, welcome to Gradify. I am Arham Doshi and let's get started. If you are new to this channel, let me tell you about this thing. This video is a part of a series called 100 Days of Code with Gradify, and it is a DSC crash course in which we will be covering 14 topics in 14 weeks. And this is the week 2 of that series, and in this week we will be covering the searching topic. So we'll be having 5 videos in this week. First one would be basically this video, that is nothing but introduction plus introduction to searching plus binary search. Another video would be like on lower bound and upper bound using binary search. Then we'll be covering what if the array is not sorted, and in that I will be covering bitonic array and ternary search. And last and the most important topic for CP and for also for placement is binary search on answer. And then we'll be covering the topics that does not belong to any particular topic, that is one of them is like kadane. So we'll be also covering such topics in depth. So let's move on. So now let's understand the definition of searching. Searching is nothing but the process of finding an item from a collection of items. Okay, so you have a bunch of items and you want to search something. That's basically searching. So what are some real life examples of searching? First one is like searching your car in a parking lot. Okay, and another thing is finding a word in a dictionary. So can you say how these two process of searching are different? So one major difference from in both of this is order. Okay, so when you are searching a car in your parking lot, the cars are presented in no specific order. Okay, so if you want to find your car in the parking lot, what you need to do is you have to look each and every car, and you have to search for your car with your number plate, and it would be a lot of hectic job. But when you are finding a word in the dictionary, what you do is maybe basically open the dictionary in the middle page of the dictionary, and if your word is like if there is a word that is like, if you are finding for a letter, let's say K, and you are currently on letter B, then you will search in the left half, and you will otherwise you will search in the right half or something like that. So the major thing when you are finding something in dictionary is the order. Okay, so when we talk about the computers, we don't have a collection of items, but we have arrays. Arrays is nothing but the collection of numbers or strings or anything. So here we have an array, and you are given a task to find the number x in the array, and if the number x is present, then return like true, plus also along with that return the index of the array, and if it is not present, return false. Okay, so how can you do it? We also knew the importance of order. Okay, so we can see here that there is no specific order in the elements of this array. So in this, what you have to do is you have to basically go through each index one and compare if that particular index is equal to x or not, and if that index is equal to x, then you can like return true and return the index, or basically return the index. And if for all the i's, after going through all the index, you don't find that x, then you can return false or maybe return -1. That is basically your way of saying that the element x is not found in the array. So let's see this in action. We will first go through the index 0 and see if this particular element at this index, that is 2, is equal to x. So it is not equal to x, so we'll just move on. We'll again see that this element is also not equal to x. We will keep going until we find an element, and at this position we will see that the element at index like 4 is equal to x, and we can just return 4. return the index, that is 4. Okay, so this is an example of what is called an unordered linear search. So why unordered? Why unordered? Because the array is not sorted. There is no particular order to the search. And why linear? So in the worst case, in the worst case of this algorithm, we have to look all the elements. That is, if there are n elements, we have to go through each, and the time complexity would be of n. So because the time complexity is of n, we are calling it linear search. So basically this is unordered linear search. So what if there would be any order to our array? So now in this case, we have the same array, but now we have an order to it. The array is sorted. So in this case again, we can try using a linear search and go through all the indices, and if we found any index which is equal to x, we can return index, and if we don't find any index, we can just return -1. But if there is a case where any element is like greater than x, so let's say instead of 12, we are like searching 13, and in search of 13, we found all these indices not equal to x, so we are just moving on. But at 15 we can find that the index is not equal to x, but at the same time the index is greater than x. So we know that all the elements that is equal to 15 or after 15 will always be greater than x. So we can say that element will never be present in this array anymore. So we can just break it here, and uh, we straight away can send -1, because we know that there won't be any element after this that is greater than x. So we can in this case we need not to search through all the elements of the array, and even if we got one element that is greater than our searching element, then we can stop it. So let's take the case of 12 here. So we can just first compare it with the element at index 2. We found that it is not equal to x. We can just move on. We are going here, here, and here, and at this point we will find that it is equal to 12, and we can just return the index of 12, that is like 3, and we are good to go. And let's say now the element is like 11 instead of 12. We will again go through this and this. We have not found our element in all this index, but when we are at the 12, we will come to know that the element at this index is greater than 11, and we can just return -1 at here, and this is saving a lot of time. We won't be comparing these two elements at all. So this is making our algorithm little bit faster. So we can call this a ordered linear search because there is an order applied to it, and this is basically little bit optimized version of unordered linear search. And why linear? Because again, if we are putting element that is greater than all the elements, let's say 30, then we will be looking at all the indexes, and the complexity would be of n. Okay, and now let's discuss a very interesting algorithm called binary search. It is one of the most important algorithm in computer science. So instead of searching elements one by one, what we can do is we can straight away search for a middle element. And let's say if we are comparing at this index, and let's call it mid, then there would be three possible cases. The case one would be obviously if the middle element is equal to the element we want to search. Okay, and in this case we can like directly return the middle element. Okay, and another case would be the middle element, the element at the middle element would be greater than x, and it could be like less than x. And if this element were to be greater than x, then we know that all the elements to the right of it would also be greater than x. Then, and we know that this all the elements to the right of it cannot be our answer, so we can like just ignore all the elements at this side, and we will only search in this size that is left of x. Okay, so in this case what we can do is we can ignore all the elements to the right side, and if this element were to be less than x, let's say 10, and if 10 is like less than 12, then we know that all the elements to the left side would also be less than 12, and we can like ignore this because this cannot be equal to 12, and our answer would be from elements to the right side of it. So we will only now search in this part. Okay, so here what we can do is we can start with a range. Initially it would be from 0 to n minus 1. In this case we have the number of elements in our array is 6, so n minus 1 is like 5, and we can progressively reduce this range. And first thing we can do is like we can take the middle element and search it with our element. So let's take this 10 and we'll search it with 12, and we'll find that it is less than 12, so we need to go to the right. So we will compress the range rate to the right. Okay, so this is our new rate. Our answer could be from this three element, and in this we will also again we will take the middle element. We will see that it is greater than 12, so these two elements can to be our answer, and we will have to see left side. So we will again compress the range to this, and we will compare it with the element, and we have found out our element, and at this position ARR of like 3 is equal to x, so we can just return the index that is equal to like 3. Okay, so we have like at first we have range like this, and at we'll be having mid that is equal to 2, and it is like less than our answer less than 12, so we'll be shifting the range to the right side. Okay, and now the new range is we have searched till here, so we will search from the next element, that is this, till the end. So the new range is like 3 to 5. Here the middle element is like 4, and it is greater than 12, so we will have to go left side, and the new range would be like we have searched till here, and our new range would be like this. So our new range would be like 3 to 3, and the middle element is also 3, and it is equal to 12, and in this case we can like return 12. Okay, so yeah, that was basically about binary search. Now let's move on to the coding part. So what I am doing is I am taking input number of elements and the elements we want to find, and currently we are having an, and then we'll be giving an array. So let's just take the inputs and let's see if it is working. So I have taken n and k, and k is the element that we want to search. Okay, and again we are taking the inputs in the array arr, and let's first see the linear search. Okay, so in linear search what we will be doing is we will be going from first index to the last index, and if we found any element equal to our index, then we can like also taking a counter element found, and initially we will be keeping it false, and if we found the element we can like make it true and say that we have found the element k at an index I. And if we have not found the element, then this would be false and we can just print that element is not found. So if we run it, we know that the 55 is at index 3, that is 0 1 2 and 3, so it is telling that it is at index 3. Now what if the array is sorted? So I'm just sorting the array, and this is the sorted array, and in this we have 55 at index like 0 1 2 3 4 and 5. 0 1 2 3 4 5. Okay, so now let's do an ordered search. Okay, so in ordered search we will be looking, we will again be going from index 0 to n. If we found the element we can like say true and return, but if the element is greater than, if we found an element that is greater than our k, then we can just break it, because no element after this would be like equal to k, because all the element will always be greater than k. Okay, so using that we found that our element is at index 5. Okay, so now let's look on to the binary search. In this what we are doing is we are like initially initiating the range with 0 to n minus 1, and we will we will run till l is less than equal to r, that is until there is at least one element. We will be using binary search, and after when this condition will be false, which means that we have exhausted our space, so we will first find the mid element. Mid element would be basically L plus R by 2, but but this is a problematic implementation, because if L is equal to the integer max and R is also equal to integer max, and adding both of them can cause integer overflow. So the better implementation is like this. It is just a way of writing, but it is overflow safe. So please implement it like this. These two are same thing, but this is a safer version. And now if we are finding the element, we can just say that we have found the element, and if the element is like less than k, then we have to go to the left side, to the right side. Now if the element at mid is like less than k, then the k would be probably the right side of it, because right side will contain all the elements that is greater than r mid. So to go right side we will be doing l is equal to mid plus 1, and otherwise we will be going left side, that is we will be doing r is equal to mid plus 1. Okay, and if we didn't found the element, we can say that we have not found the element. So in binary search also we have found the element at index 5. Now let's see an interesting implementation of the binary search. This is basically an efficient implementation in which we will be using the jumps. So at first we will be starting with n by 2 as a jump. Then as we move closer and closer to our answer, we will be shortening our jumps. At first we will be having n by 2 as the jump, then we'll be having n by 4 as the jump, and then n by 8 as the jump, and so on. So and at last the jump would be equal to 1. So we will like start our answer would with 0. We'll try to jump to the n by 2 size. If this element is like less than or equal to k, then we will like jump here and we will try to jump further. Otherwise we will be staying at our answer and we will be trying a shorter jump, and by successively shortening the jumps we will get the answer. So in this case we will be first starting with the jump equal to like 3, that is n by 2, and we are like getting well as the answer. Now the jump would be like uh, equal to n by 4, that is equal to 1. We will try to go here, but it is greater than 12, so we will not go there, and after that we can break it. And if our element is present, then we will find that ARR of answer is our element. Okay, and this is implementing the binary search in just 2 lines. So see how easy this is to implement than this. Okay, so yeah, that was it. So now let's discuss a particular problem. This problem is basically in the Hacker Earth series. In this, they are given a tutorial of the binary search, and below the tutorial, they are giving one problem to uh, help you to understand the concept. So I highly recommend you to implement this question. Okay, I will be sending the link in the sheet. So if you are not aware about the sheet, along with these videos, we are maintaining a sheet, and in that case, in that I am sharing one daily problem for placements and one problem for CP, and with that I am also sharing the resources in that sheet. And happy coding. If you like the video, smash that like button, and until next time, bye.